Hello everyone. So in this video we are going to discuss about the properties of the continuous time Fourier transform. We have already seen some properties related to Fourier series, and we will see the equivalent properties for Fourier transform as well in this video. So why we basically interested in understanding the properties of any kind of phenomena? So properties basically provide insights about that phenomena. So in this case, the properties of continuous time Fourier transform provides insights about the transforms. So what it will provide the information about? It will give relationship between time domain and frequency domain description of a signal. So it will provide a relationship among time domain and frequency domain. And also it helps to reduce the complexity in evaluating Fourier transform or inverse Fourier transform. So it will help to reduce the complexity for calculating the Fourier transform and inverse Fourier transform. So there are various signals which is in itself are in complex form, and the evaluation of Fourier transform of those signal are itself complex. So using this property we can reduce that complexity. So before going in depth of the properties, we will first write the Fourier transform pair so that you will get a better understanding of all those properties. So we have already discussed about the Fourier transform pair. So a signal xt can be represented as 1 over 2 pi minus infinity to infinity x of j omega e raised to the power j omega t d omega, and x of j omega is represented as minus infinity to infinity xt e raised to the power minus j omega t dt. So this is the inverse Fourier transform equation, and this is the Fourier transform equation, and together they are called the Fourier transform pairs. So these are Fourier transform pairs. So in a nutshell we can say that xt is a signal whose Fourier transform can be represented as x of j omega, and similarly if x of j omega is the Fourier transform representation, xt is the inverse Fourier transform of x of j omega. So we will use this convention very frequently, so that's why I am explaining in a short. So let's start to discuss the first property. So the first property is the property of linearity. So we will discuss about the linearity. So it is analogous to what we have discussed in the Fourier series part. So suppose xt is a signal whose Fourier transform is represented as x of j omega. Yt is another signal whose Fourier transform is represented as y of j omega. Then the linear combination of these two, a of xt plus b of yt, must have the Fourier transform of the form a into x of j omega plus b multiplied with y of j omega. So multiplying with a scalar and adding has the same effect in the frequency domain itself. So this is the property of linearity, and these two property, like multiplying the scalar is called the homogeneity property and adding them is called additive property, and it is following both. So this property is explained by this form. And we'll further see some examples to understand it better in later part of this video. So now I'll discuss another property, that is time shifting. So we'll see the effect of Fourier transform when we shift the signal in time domain. So suppose xt is your signal in time domain, so and xj omega is representing the Fourier transform of this signal, and suppose we shift our signal in the time domain. So we will be doing xt minus t naught. So what is the effect at the frequency domain? It will be e raised to the power minus j omega t naught multiplied with x of j omega. So there is a one factor added to the earlier form, that is e raised to the power minus j omega t naught, and we'll see, like, we'll do a short derivation to understand how it came when we shift the signal in time domain. So we have already given the representation for the xt. So xt can be represented as 1 over 2 pi minus infinity to infinity x of j omega e raised to the power j omega t dt, sorry, d omega. Now what we'll do, we'll shift the signal xt minus t naught. So what will be the effect in this expression? We have to replace the t with t minus t naught. So now here j omega, t is replaced with t minus t naught, that will be d omega. Now we'll expand this. So what will happen? We can write it as 1 over 2 pi minus infinity to infinity e raised to the power minus j omega t naught multiplied with x of j omega e raised to the power j omega t d omega. So now here is some property which I want to discuss, that in this case x of j omega and xt forms a Fourier transform pair. So xt was the signal and x of j omega was the Fourier transform of that signal. In this case, and other forms are equivalent, like we have an e raised to power j omega d omega. So if we compare this equation, suppose I mark it as equation number 1 and this equation as equation number 2. So if we'll compare equation number 1 and equation number 2, what you will get, as xt was the Fourier transform, xt Fourier transform is x of j omega. So the Fourier transform of xt minus t naught is e raised to the power minus j omega t naught x of j omega. So this is like, these form a transform pair as these are forming a transform pair. So here we can conclude that the Fourier transform of x of t minus t naught is equivalent to e raised to the power minus j omega t naught x of j omega. So this derivation shows that this is the Fourier transform of a time shifted signal in time domain. So as you can see, the magnitude is not changing. If you take the mod, then the magnitude of original signal and the time shifted version in the frequency domain will be same, but there is only a change in phase. So this time shifting provides a phase shift in the, so it will provide a phase shift which is equivalent to minus omega t naught. So only phase is going to change, magnitude will not change. So now using these two property, we'll solve one example to understand how this property can be useful in getting Fourier transform of complex signals. So suppose we will express a signal xt in the form of 1 over t x1 t minus 2.5 plus x2 t minus 2.5, and here with x1 we mean that it's a rectangular signal which is having value varying from minus 1 by 2 to plus 1 by 2, and it will take a value of 1 in that range, and this is your x1t, and x2t is shown by a pulse which is taking a value of 1 for the period minus 3 by 2 to 3 by 2, and this is your x2t, and your xt is the linear combination of these two signal, and that is also multiplied with some scalars. So the equivalent xt can be represented like this. So it will be 1, 2, 3 and 4. So your signal will be like this form. This can be easily like deduced. You can plot in MATLAB or any other software as well, and you will find that this will be your x of t. So this is the graph of x of t. So now we will going to get the Fourier transform of xt, which is the combination of these two signal x1t and x2t, and we will use the property of time shifting and linearity to find the Fourier transform of this signal. So now we will first solve for x1t, that is the Fourier transform of x1t is represented as x1 j omega, and that can be represented using the form minus infinity to infinity x1t e raised to the power minus j omega t dt. And as the graph of x1t, we have already shown that it is varying from minus 1 by 2 to 1 by 2, taking value of 1 for this t. So the limit will be from minus 1 by 2 to 1 by 2, and it is taking value of 1, and it is multiplied by e raised to the power minus j omega t dt. Now you can solve it easily. I am just giving the final form. So the final form of this will be equivalent to 2 sine omega by 2 divided by omega. So you can have the integration which will be of the form like e raised to the power minus j omega 1 by 2 minus e raised to the power plus j omega by 2, and that will be like minus j omega, and by rearranging this form you can get this final result. That is very easy, you can try, but I am giving here the final form of x1 j omega, which is 2 sine omega by 2 divided by omega. Now I'll take the second function, that is your x2 of j omega. So this is the Fourier transform of the second signal, and it is varying from minus infinity to infinity, integration x2 e raised to power minus j omega t dt. Now we'll put the limit. Now for the other signal, the limit is from minus 3 by 2 to 3 by 2. It is taking a value of 1 in that range. So now we'll put the limit minus 3 by 2 to 3 by 2, and it will take a value of 1 e raised to the power minus j omega t dt. And again you can do the same maths, and you will get a final form of sine 3 omega by 2 divided by omega. So this is your x2 of j omega. So we have our x1 of j omega as this expression, and we have our x2 as this expression. Now what we have to find, so this expression which we have as of xt, it is basically we have to multiply a scalar of 1 by 2 in the time domain to that x1 signal, and then we have to shift that signal with 2.5. So what will be the equivalent Fourier transform? We have to just multiply this same scalar with the Fourier transform. So it will be your 1 by 2 x of x of j omega, and that x of j omega will be multiplied by e raised to the power minus j 5 omega by 2 because of this shift. And similarly for the second case, though there is no scalar multiplied, so you have to just take the x of x2 of, so this will be x1, so x2 of j omega, and that will be multiplied with e raised to power minus j 5 omega by 2. So we'll just write it as a final form. So the final form of the Fourier transform of xt will be equal to x of j omega, and that will be e raised to power minus j 5 omega by 2. We have to just add these two signals, sine of omega by 2 plus 2 sine 3 omega by 2 divided by omega. So this is the final form. So here we use both the property, that is your linearity. So we have adding two signals, and they are also multiplied with some scalars, and then we have also doing the shifting property. So here both of the signals are shifted with some of the amount. Here in this case both time shifts are identical, but we can take any of the combinations or any of the time shifting values. So so you can see that how easily we got the Fourier transform of this signal using linear combination of these two signals plus the time shifted version.